Good afternoon. Thank you again for allowing me to come up here and talk to you a little bit about hydrogeology. I've been, as Steve mentioned, I've been working in Texas since about 2003, working with the groundwater in groundwater here. And the way I wanted to just kind of start it off was just, there's typically several questions that are pretty common that we run into. Questions like, how much water am I going to be able to pump? And, we'll hear that from a well owner or somebody's getting ready to put in a well. Another common question is going to be, well, how's, this guy over here, he's putting in a well. How's that going to affect my well? What can I expect to happen? Am I going to lose my ability to pump? Or just how long will my well last? How long that water's going to be there? What's my water going to taste like? What's that quality? Is it going to have a weird smell to it? So these are some common questions that we get about groundwater and about the hydrogeology. And it really comes down to a question, really, of groundwater availability. So that's the way we're going to really kind of try to talk about it a little bit today, is look at this question of groundwater availability and what that means from a hydrogeology perspective. There's several factors that can go into affecting how groundwater availability, how much groundwater we say is there and can be used. You get the structure of the rock, the geologic structure, how it's dipping, whether there's faults, how thick that formation is, how deep it is. There's also the type of rock, whether it's a sandstone or a limestone, granite, fractures, a lot of different things that go into the different types of rock type and the structure there. And then there's the hydraulic properties that go into it, and things like terms, I'll go into these here in a little bit, with permeability, porosity, so you get a little bit of a vocabulary lesson today also. But some of those other hydraulic properties, think about just water levels and recharge, how much water is coming into the aquifer. What are some of the boundaries that could be encountered there? Then there's those existing users that are out there, people that are already pumping, where the locations of those wells are, when they're pumping those wells, how much they're pumping. So you have those existing users, that's a consideration in the availability. And then, of course, the water quality, as I mentioned, how that water is moving through and dissolving the rock, and how those constituents are affecting the water itself. And then there's the regulatory framework, which you've heard about today as well. Well, we're going to focus really just on those first four when we're talking about Hydrogeology 101 here. So looking at those first four factors, we're going to kind of talk about them a little bit. Now, of course, I'd be remiss if I didn't talk first about, well, what's the water cycle? Water gets evaporated from the oceans, you get your nice clouds, get some rain, not recently, but you do get some rain occasionally. That's going to flow down. It's going to be captured by plants, captured by trees, stuck to the leaves, re-evaporated, flow through streams, caught in rivers, and then, of course, some of that water is going to seep into the ground through these recharge areas, and then it's going to start to flow through those rocks. So that's really what we're focused on today, is looking at that groundwater, just that groundwater portion of the water cycle. So as I mentioned, you'll get a little vocabulary lesson today. I'm going to give you, these are kind of the main terms I'll be mentioning and talking about a little bit. There's some very simplified definitions. So if there's any other hydrogeologists, I recognize that these are simplified definitions. But when we're looking at permeability, that's a term that's really just used to go, well, how easy is it for some type of fluid to move through that rock? And then the porosity part of it is, well, how much water can be stored inside that rock? So how much of that how much open space there is inside of a rock? Hydraulic conductivity takes that permeability value and then it incorporates what the water's like. So you take permeability and then you look at the density and the viscosity of that water, bring those together in order to get the hydraulic conductivity. So that's a value that can actually change very much. Even if you have the same permeability in a rock, you can have different hydraulic conductivities in different locations. And then there's transmissivity of an aquifer, which is just the hydraulic conductivity multiplied by that thickness of the aquifer. And then these last two terms, the storage coefficient and specific yield. Storage coefficient is usually a term that we usually use just with pressurized aquifers. And I'll get into what that is here in just a moment. but it's just that deals with the part that's stored just as pressure within the system. And it's typically a very small value. But specific yield, that's related to the porosity of the rock. And it's a ratio of how much water would just, if I were to pick it up, how much water drains from that rock to, say, fill the glass versus how big the rock itself is. So there's a couple of different terms there. Now, you've all seen these maps before, I'm sure. There's 9 major aquifers, 22 minor aquifers out there, all of them different lithologies, different rock structures. The permeabilities, hydraulic conductivities throughout these are different. So all of these have different, very different characteristics that we have to look at when we start thinking about, well, what's the water available from these rocks? How does it move? Many of these aquifers fall into these two categories. When you're looking at the structure, you get a confined aquifer or an unconfined aquifer. And what we're looking at there is the confined aquifer is it's essentially an aquifer, a permeable unit of rock that's sandwiched between these 2 layers of other rock that water doesn't get through very easily. So it's got that formation squeezed between it, water's moving down it, and it gets pressurized, like you would think of a hose. You poke a hole in the hose, water squirts up. Well, it does the same thing in these aquifers. When you put it in a well, the water level then rises above the top of the aquifer. Whereas with an unconfined aquifer, that's where you get an aquifer much like the Ogallala. Water is essentially at atmospheric pressure, so it's not a pressurized system. Water is stored just in between the sand grains there, and generally follows what the surface topography looks like. And then, as I mentioned, you have different rock types. If you have a sand and gravel, for example, like the Carrizo or the Gulf Coast aquifer systems, that's where you get these aquifers that they have really good permeability and really good porosity. They can store a lot of water, and the water moves through it very easily. You then can move into a system, say you go to a limestone system like you have down here in San Antonio with the Edwards Aquifer. It has a really good permeability. Water's able to move through those fractures and those caves. It can move through it really fast. But compared to a sand and gravel aquifer, it has a much lower porosity. Where it does have porosity, it can be huge, big cave, but it's not as consistent and it doesn't store as much water, which is why you see these rapid fluctuations in water level within the aquifer. That's still really good aquifer material. Well, then you have a clay or a shale. And with these types of formations, there's a lot of porosity, a lot of open space between those clay minerals, but water doesn't move through it very well at all. So it's a very poor aquifer material. Bad permeability, but really good porosity. So let's look now at the hydraulic properties that I had mentioned. Well, we owe that really started with a guy named Henry Darcy. And this is, I promise, it's the only math formula you get. So you don't have to do a lot of math today. But this was his, what he came up with in doing research and doing some experiments there in France. He found that you get the correlation between groundwater flow, which he used as Q. So that's the flow of the water. And you can determine that flow through the hydraulic conductivity, that K value, through the hydraulic gradient, which I'll discuss that in a moment, that's that I value, and then the area through which it's flowing. So using these 3 parameters, we could figure out, or 3 variables, we could figure out, okay, what's the flow through that aquifer? And looking at that in say just at an aquifer itself, this is where we can go, okay, we've got 2 wells, spaced some distance apart, and different water levels in each of those wells. Well, we just subtract those 2 water levels, divide by the distance, and that's our hydraulic gradient. So then we know what that I value is. We can do tests to determine what that K value is, know what the hydraulic gradient, or know what the hydraulic conductivity is. And then just looking at that cross-sectional area, and well, there you go. We have everything we need to know how water moves through that aquifer. So to make it a little more practical, we go, well, okay, what about wells? We can understand how it's moving through the aquifer. What about a specific well? Well, we can look at the specific wells using these variables also. Now, as we saw from the Darcy's law, you have a gradient. One of the requirements for water to flow through that aquifer is that there has to be a difference in water levels. And that's what we create when we start to pump a well, is this gradient around a well. And that's called the cone of depression. And this is an example up here of a well, for example, that it starts pumping, say 10 gallons a minute, it just starts drawing down water levels right there around the well. Well, in order to be able to determine how much that drawdown is, so what that effect would be, all we need is that pumping rate that I mentioned, the transmissivity, which is just the hydraulic conductivity and the thickness of the aquifer, the storage coefficient, which we know is for an unconfined aquifer, it's typically between 0.1 and 0.3. For a confined aquifer, typically between 0.001 and something less. So pretty small numbers there on the storage coefficient. How long it's going to be pumping. And then we can just determine, okay, at different distances, what's that difference, what's that effect going to be? And you go, okay, well, you have that question of the existing user going, well, what's the effect of somebody else when they want to put in a well near me? Well, we can just add those basically to both of those computations, add them together, and we see that we start to see the differences in how groundwater is being affected and how those water levels are being affected when we start getting multiple wells pumping together. And this is a term that you'll hear called interference drawdown. It's how one well interferes with the other to create water level declines. A lot of different ways that we can calculate this. This was done very simple method. You can do that as an analytical calculation is what we call it. A good example of that is a formula called the Theis Equation. It's something you can do very quick, very easy. It's Microsoft, throw it into an Excel spreadsheet and it spits out an answer for you type thing. Or you can decide to get extremely complicated with the numerical models, and you've probably heard about the Water Development Board's GAMs, the Groundwater Availability models. These are numerical models built on large grids where they basically chop the aquifer up into little pieces and look at what are going to be the effects through simulations of the groundwater flow. But it still all comes back to that simple formula. So when we can see here what the water level changes are going to look like, and you're going to go, well, okay, what does that mean? One of the other questions we seem to hear sometimes is, what does that mean? Are we depleting the aquifer? What's that change really doing as far as the storage change in the aquifer? Well, in an unconfined aquifer, as I mentioned, you get a relatively high specific yield. So a 15%, it's usually going to vary somewhere between 10% to 30%, being that ratio of the volume of water drained to the volume of the rock. You get water level, it's at an atmospheric pressure. And so what you get is you get more water for a smaller change in water level. I'm going to show you an example here with a 10-foot by 10-foot column. Specific yield of 0.15. Get some water out of it, causes that little red line that just showed up on the top there. Can barely see it. So to get this volume of water, you had 1/2 inch of drawdown. Your fish is still happy in his water cooler, still sitting there swimming around. Well, let's look at a confined aquifer, though. We got a lower storage coefficient, 10 to the -4, 0.0001. Your aquifer is under higher pressure, so what you see is a greater change in water level for less water. So we're taking out the exact same amount of water out of our column, but in this case, you get quite a bit of decline in order to get that same amount. In fact, we're looking at 67 feet of drawdown to equal that 5 gallons of water that we were looking for. So you can see there's big differences in how the structure and how the type of the aquifer properties look like there. So now let's look at the question of water quality. Water quality, we're looking at, okay, we're really going to focus on the total dissolved solids of the system. And total dissolved solids, when we're looking at water quality, is how much of all the different things that have been dissolved into the water, all the different constituents of the rock, how much do those add up to? Anything less than 1,000 within Texas is considered fresh water. I was actually talking to a colleague of mine from up in Colorado, and his comment was that he couldn't believe that we allow it to go up to 1,000. I was like, well, it's pretty common around here. But for them, it's 500. Anything more than 500 is considered really bad. But it's just that different types of rock, how they really affect the water quality. If you're running water through, for example, through gypsum, that's where you're going to get that sulfur smell. It's going to release different components, and it dissolves very easily. Same with halite or salt. But if you're running it through a granite type formation or a fractured granite, the igneous type rocks, it doesn't dissolve as fast, and you get really better lower TDS water. So one of the takeaways from water quality, though, it's important when you're thinking about it from the board perspective of going, okay, how do we put rules in to make sure that wells are going to be completed properly in order to verify that we're not getting mixing within the borehole or within the annular space, so that you're not getting commingling of waters within that space to preserve the water quality. So just a quick summary here. Yes, groundwater is, as you know, it's going to continue to be a very important source of water in Texas. There's some of these basic principles of hydrogeology, thinking about the groundwater availability, that, you know, knowing some of these principles, understanding how water flows a little bit, it's going to help you determine, you know, what's available for those different uses and for the different proposed uses. And then I just wanted to also leave you with a couple of other resources. I know this was the quick 20-minute version of talking about groundwater availability. The Water Development Board has a couple of great educational videos out there on their website for looking at describing aquifers, giving a little quick summary. I think they're about 5 to 10-minute videos. National Groundwater Association, they also have some good options out there for some educational material. And with that, I'll go ahead, and Steve mentioned, might be questions at the end, so to keep it going forward. Yep.
I appreciate that. Greg, where are you? Thank you very much.